Okay, next we are going to talk about adjoint operator. Look at here. Uh, Suppose that H is a Hilbert space and T is a bundle linear operator on H. Then by theorem, here I said C1. This means the textbook, the functional analysis textbook by Rudin, or any other textbook. Anyway, by theorem, there exists a unique operator on H. Okay, it means unique element of B of H, usually denoted by T star, such that we have this. The inner product of TH and K equals the inner product of H and T star K. Okay, for all elements H and K in H. This operator T star, the bundle linear operator, this element of BH, T star, is called the adjoint of T. Okay, it's called the adjoint of T, and we have this, that the norm of T star equals the norm of T. I leave it to you to figure out, okay, as an exercise. However, you may refer to textbooks to figure out about this. And this means that corresponding to every bundle linear operator on a Hilbert space, there is an adjoint, or simply I have to say, we can say every bundle linear operator on a Hilbert space is automatically adjointable. Okay, it means the adjoint automatically exists. And if you want to find the adjoint, this characterization, actually this equation is the characterization of the adjoint operator. This equation must satisfy. It means, look at here, I prepared some note for you. It means if you want to find the adjoint of the bundle linear operator, you have to find an element. It means another bundle linear operator like S, such that this equation, which is the characterization of the adjoint, satisfied. If this satisfied, then S must be the adjoint of T. Okay, like this. It means we have to find S such that this is true. Then this means S must be the adjoint of T. Okay, let's back here. Starting with some example, the first example here. The adjoint operators on find. Okay. You suppose that we have a bundle linear operator on a finite dimensional Hilbert space. Let's say on a n-dimensional Hilbert space. Okay, and we know that Hilbert space is automatically Cn. Okay, here's my point. Let me show you here. If you have a bundle linear operator on a finite dimensional Hilbert space, this bundle linear operator corresponds to a matrix, right? Okay. Now we know that T has a unique adjoint, T star. So this T star is also a bundle linear operator. But what is the matrix of T star is A star. But what is A star? What is the connection between or relation between A and A star? This A star is actually the conjugate transpose of A. Okay. So simply, if the matrix of T is A, the matrix of the adjoint of T, which is denoted by, the matrix of the adjoint of T, it means T star, which is usually denoted by a star. This A star is the conjugate transpose of A. Conjugate transpose of A. You can see here. For example, look at this. This is a matrix, 2 by 2 matrix. You can see here. So this matrix corresponds to a bundle linear operator on C2. Okay, like T. Now, this T is automatically adjointable, right? So we have T star. So the matrix of T star is denoted by A star. But what is that A star? you can see here the conjugate transpose of A. It means like first we take conjugate here, so this becomes 2 minus I. Same, minus 1, 3, and this one becomes I. Then we take transpose. When you take transpose, I comes here, this comes here, and this comes here, this comes here. So you get this. A star becomes 2 minus I, 3 minus 1 I. So A star is conjugate transpose. You can take conjugate first, then transpose. Or you can transpose first, then you take conjugate. So you get A star, which is the matrix of T star, and T star is the adjoint of T. Okay. Look at the next example. Okay, in the next example, we are going to talk about the adjoints of scalar operators. What does it mean? You suppose that H is a Hilbert space and alpha is a non-zero scalar. Okay, in the lecture note, I think I wrote lambda. Please correct it. This is alpha. Okay, this is correct. You suppose that T is a bundle linear operator on H corresponding to this alpha. Actually, T is a scalar operator corresponding to alpha. What does it mean? It means T maps every H to alpha H. Okay, you can see that this is a bundle linear operator on H, a scalar operator, because you can see H is mapped to a scalar product. H is mapped to the scalar product of H by alpha. That's why it's called scalar operator. We can show that T is a bundle linear operator and the norm of T is the absolute value of alpha. I leave it to you to figure out, okay? Now, what is the adjoint of T? Okay, what is the adjoint of T? T star. Of course, is a bundle linear operator. Is given by, look at here, T star, H equals alpha bar H. Alpha bar is the conjugate of alpha. It's interesting. Look at here, T is corresponding to alpha. T star, the adjoint of T corresponds to alpha bar. Of course, because this one is easy, I'm gonna leave it to you, but the next example I explain more. It means if you want to find the formula of T star, okay, you have to show that this characterization, this equation is satisfied. Okay. Next, look at here. We want to find the adjoint of forward shift or the unilateral shift. Do you remember we already talked about this bundle linear operator T on how to say? Yes, we talk about the this bundle linear operator on L2. T from L2. Okay, T on L2 is defined to be like this, right? Which is called unilateral shift or forward shift. Okay, it is a bundle linear operator on L2. Now we want to find the adjoint of T, okay, which is denoted by T star. We claim that the adjoint of T star is given like this. Look at here, T star maps every element here to this. Look at here, T star of x1, x2, x3 equals x2, x3, x4. It's kind of backward shift, okay? Look at here, this is like forward shift. T star is backward shift. Of course, we have to show that this is indeed the adjoint of T, right? Okay. We are going to show this, that this T star satisfies this characterization. Okay, let me show you. Okay, we are going to check that why T star is this, okay? I have done here for you. Look at here. Yes, we want to show that the adjoint of the unilateral shift T is T star, which is backward shift. Okay, look at here. We define an operator on L2 like this: S, which maps x1, x2, x3 to x2, x3. Okay, a kind of backward shift. Okay, I leave it to you to see that S is actually a bundle linear operator on L2. but we want to show that S is the adjoint of T. Okay, it means this equation, which is the characterization of the adjoint operator, must satisfy. Okay, it means we must have the inner product of Tx and Y equals the inner product of X and S of Y, okay, for every X and Y in L2. Okay, if you calculate this, you can see the left hand side and right hand side are equal. Okay, I leave it to you. The left, okay, here T of x1 x2 becomes 0, x1 x2. Now if you calculate the inner product, become this, and this right hand side S of y1 y2 y3 becomes like y2 y3, and if you calculate the inner product of these two, becomes this. Okay, I leave it to you to check. It's very easy. So you can see the left hand side and right hand side are equal. Okay, so this means that, okay, this operator S satisfies the characterization of adjoint operator. So it means this S must be T star, the adjoint of T. So the adjoint of T is definitely is given by this. Now look at the next example. Okay, look at the next example. Suppose that alpha 1, alpha 2, this is a sequence of bonded, okay, bonded sequence of complex numbers. Okay, it means the absolute value of each alpha I is less than a positive number. Okay, bonded sequence. Now we define an operator on L2 by this. T maps every sequence like x1 x2 to alpha 1 x1 alpha 2 x2. You can see a kind of multiplication operator. Each xi is multiplied by alpha I. Again, we can show that, I leave it to you to check that T is a bonded linear operator on L2. Now, what is the adjoint of T? Okay, what would you think about the adjoint of T? T star is a bonded linear operator. The adjoint of T. Okay, what is the formula of T star? Okay, the answer is this, and I leave it to you to figure out or to prove that T star indeed equals this. Look at here. We can say like this. Look at here. T corresponds to this sequence, right? So T star corresponds to this sequence. Look at here, alpha 1 bar, alpha 2 bar. It means T star is given by this formula. T star maps every x1, x2, this sequence to, look at here, alpha 1 bar x1, alpha 2 bar x2. So you can see each xi is multiplied by alpha I bar. Okay, so I leave it to you to show that T star sorry, let me repeat. I leave it to you to show that this T star is indeed given by this formula. Okay, it means you have to show that T star satisfies the characterization of the adjoint operator. Okay, next we have a definition here which is very important. Let's say T is a bonded linear operator on a Hilbert space H. Okay, we say that T is self-adjoint or Hermitian, okay, if T star equals T. It means the adjoint of T equals T. We say T is a normal operator if T star equals T star T. It means T commutes with its adjoint. We say T is a unitary if T star T equals T star equals identity operator. What does it mean? It means that the inverse of T is T star. And we call it a projection if T squared, it means TOT, the composition of T bit itself, equals T. So bear in mind, this is a very important definition here. And look at here, we said that it is easy to see that actually every self-adjoint operator as well as as well as every unitary operator is normal. Okay, I leave it to you to check. It's very easy that every self-adjoint operator is actually normal. Okay, and every unitary operator is also normal. Okay, it means you can show that the adjoint operator here satisfy this, and unitary operator, this is very clear actually, is a normal operator. So this is easy to check. I leave it to you. Okay, now let's see some example here. Okay, look at this example. Suppose that this is a sequence of this is a bounded sequence of real numbers. Okay, of real numbers. It means each alpha I is a real number. Do you remember, according to this sequence, bounded sequence, we can define a bounded linear operator on L2 by multiplication, something like this. If you remember, just now we talked about this. We claim that this operator T is self-adjoint and therefore normal. Okay, why is it like that? Okay, we have to okay, we claim that this is self-adjoint, right? So it means T must be equal to T star. But why is it like that? Do you remember how to get T star? If you remember, we just talked about this. We said that T star is given like this, right? Alpha 1 bar, x1, alpha 2 bar, x2, and so on. But look at here. Here, each alpha I is a real number. So the conjugate of each alpha I equals alpha, right? Because they are real number actually. So this becomes alpha 1 x2, alpha 2 x2, and so on. And what is this actually? This is T of x, right? So from this discussion, you can see that T star equals T. So what does it mean? It means T is a self-adjoint operator, and definitely automatically is normal, right? Because when T star equals T, so it is easy to see that T star commutes with T, or T commutes with T star. Okay. And the next example. Okay, here. Okay, look at this example. U is defined to be a scalar operator on L2 corresponding to this scalar I. Okay, it means U maps every x to ix. Okay, a scalar paradigm of x. So U is kind of a scalar operator that we talk about. So we claim that U is a unitary operator and therefore normal. So why is it like that? If it is unitary, it means U star, U must be U star equals identity operator. I've done it here for you. Look at here. So this is U, right? If you remember, U star is given by this. It means U star is also a scalar operator, and U star, okay, I forgot to put here. Let me do it for you here. This means U star x. Okay, there is a typo. U star x. Okay, if I delete here. Okay, let me make it a bit better for you. Okay. Okay, U star. Okay. U star. Okay. U star x equals I bar x. Okay. And now let's check. U star at x equals U at U star x, and look at here, you take this U star like y, so uy equals I y. Okay, but our y is U star x, so this equals I, and U star x is I bar x, right? And this equals the absolute value of I squared x, and the absolute value of I is 1, so this equals 1x, and this can be written as ix, identity operator. So you can see U star equals I. Similarly, I leave it to you. You can show that, I leave it to you, this one. U star U is also equal to identity operator. So this shows that U is a unitary operator. Look at the next example. Let's suppose that P on L2 is an operator. You can is an operator defined by this. Okay, P maps x1 x2 to x1 0 0. Okay, we can show that P is a bundle linear operator on L2. But actually, we can show that P is a projection. Okay, P is a projection. Actually, P is a projection of L2 onto one-dimensional subspace of L2, which is automatically isomorphic to C. Okay, so it means, look at here how it is acting. P maps every sequence, every element of L2 to this x1 0 0. So it's a projection onto one-dimensional subspace of L2, which is automatically isomorphic to C. Okay, and of course it is easy to show that because we claim that P is a projection, right? It is easy to see that P2, it means POP equals P. So I leave it to you to check. It's really easy. You can show that P2 at X equals P at X, and that equals this. It means P2 at X1 X2 equals P at X1 X2, and so on, and this equals X1 0 0, and so on. So I leave it to you to check. Okay, so P is a projection. Okay, next we have a theorem that we just mentioned without proof. The proof is not required, but we need this theorem for the next theorem. Okay, look at here. Let's say T is a bundle linear operator on a Hilbert space. Suppose that T is normal, okay, normal operator. Then T is invertible if and only if there exists a positive number like delta such that the norm of TH is greater than equals delta the norm of H for every H in H. So bear in mind, this is true if T is normal. So the proof is not required, but we just mentioned this theorem without proof because we need to apply this for this theorem. So bear in mind. Now, theorem 4.11, which is very interesting and important. Listen very carefully. Let me read for you first, then we discuss the proof. Suppose that T is a self-adjoint operator. It means T star equals T. Okay? It means T star equals T. Then the spectrum of T is a subset of real number. Okay, so if T is a self-adjoint operator, the spectrum of T, okay, the spectrum, you know that the spectrum in general is a subset of complex number. But for self-adjoint operators, the spectrum is a subset of real number. It means every element of the spectrum is a real number. And the other one, which is talking about the spectrum of unitary operators. Look at here. Okay, but let me see here. If U belongs, okay, it's a unitary operator, then, okay, I think there's a typo here. Let me fix it. Okay, guys, there was a typo here, so I fixed it. So you also please fix it in your lecture note. It was a small typo. So the second statement, if U is a unitary operator and lambda is an element of the spectrum of U, then the absolute value of lambda equals 1. This simply means that the spectrum of U is a subset of unit circle. This T, unit circle, it means you can see here, all scalars such that the absolute value of lambda equals 1. So in complex plane, this actually, this T, be denoted by like this, is a unit circle. So this simply means that this is a unit circle centered at origin. So this means that if U is a unitary operator, the spectrum of, if U is a unitary operator, then the spectrum of U is a subset of a unit circle, which means this. And of course now we fix it. When we say lambda belongs to U, then the absolute value of lambda equals 1. So it means lambda must belong to this set. Okay, now let's prove it. First A, then B. Okay, let's start the proof starting with A. Okay, so suppose that T is a self-adjoint operator. It means T star equals T. Okay, and suppose that lambda is an element of a spectrum, and this lambda in general is a complex number, so it can be written as alpha plus I beta. Alpha and beta are real numbers. So you define T lambda to be T minus lambda I. Here I said by a simple calculation we can show this. Okay, I said by a simple calculation, but actually the calculation is quite long, so I'm gonna skip it. So do not worry, in the exam I will not ask you, but at least bear in mind. Okay, if you had time you can show this. Okay, but I will not ask you in the exam. So you can say that by some calculation we have this, the norm of T lambda h squared equals the norm of th minus alpha h squared plus beta squared, the norm of h squared. Okay, so from this we have this is greater than this, right? Okay, so if you take the square root, we get this, the norm of T lambda h is greater than equals the absolute value of beta, the norm of h. Okay, because look at here, this is the sum of these two, so definitely this is greater than this. This one is greater than this one. So if you take a square root, you get this. If you take a square root on both sides, you get this. Now look at here. Our goal is to prove that lambda, which is an element of the spectrum, is a real number, right? So if we want to show that lambda is a real number, we have to show that beta actually is 0. Okay, so suppose the otherwise, like if beta is not 0, so lambda is a scalar, is a complex scalar. So if beta is not 0, which is equivalent to saying that lambda is a complex scalar, you can see here, which means lambda does not belong to R. Okay, then since T lambda is a normal operator, why is it normal? Just let me give you some indication. Okay, you have to show that T lambda star, T lambda commutes with T lambda star, right? Let me give you some indication. This is T lambda, right? We can show that T lambda star equals this. Look at here. This equals T star minus and the adjoint of lambda I, which is a scalar operator, becomes lambda bar I. And look at here, since T is a self-adjoint operator, T star equals T. Okay, become T minus lambda bar I. So this is T lambda and this is T lambda star. You can see here. So this is T lambda and this is T lambda star. Then this is easy. I'm gonna leave it to you to check that this is true. Okay, so this means that T lambda is normal. Okay, so T lambda is normal, right? Now look at here, we are going to apply this theorem, this theorem 4.10. Okay, we are going to apply this. By this theorem, okay, look at here, T lambda is a normal operator, and the norm of T lambda h is greater than the absolute value of beta is a positive number, the norm of h. Okay, so therefore, look at here, therefore by this theorem, look at here, by this theorem, you just apply this theorem for T lambda. You can see here. So T lambda is normal such that we have this. This implies that, look at here, this implies that T lambda, okay, this implies that T lambda is invertible. Okay, T lambda is invertible. Okay, look at here, T lambda is normal and we have this. If you apply theorem 4.10, this implies that T lambda is invertible. When you say T lambda is invertible, what is T lambda? Is this T minus lambda I. So when T minus lambda I is invertible, it means lambda does not belong to a spectrum of T. So this is a contradiction, right? This is a contradiction, and this contradiction is coming from this assumption. When we suppose that beta is not 0, we get contradiction. So beta must be 0. So when beta is 0, look at here, so lambda becomes a real number. So this is true that if T is a self-adjoint operator, every element of a spectrum is a real number. Okay. So this is the proof of A. Okay, now we want to prove B. Okay, look at here. We want to show that okay, U is a unitary operator. We want to show that the spectrum of U is a subset of the unit circle. So first of all, since U is unitary, then the norm of U equals 1. Why is it like that? Again, this one is not difficult. I leave it to you as an exercise, okay, to check that the norm of U is 1. And okay, now we are going to prove this, right? We are going to prove this. So you suppose that lambda is an element of the spectrum of U. Therefore, if you remember by this theorem 3.14, the absolute value of lambda is less than or equals the norm of U, and the norm of U is 1. So we have the absolute value of lambda less than equals 1. But we want to show that the absolute value of lambda equals 1. Okay, so far we know that this is equal, less than or equals 1. Okay, so we want to show that less than 1 doesn't happen. So it must be equals to 1. So if the absolute value of lambda is less than 1, okay, we know that less than or equals 1. But if it is less than 1, then the norm of lambda U star is less than 1. Why is it like that? It is easy. I have done it here for you. Look at here. The norm of, okay, here. Yes. The norm of lambda U star equals, by the property of the norm, the absolute value of lambda, the norm of U star, and this equals the absolute value of lambda. Do you remember the norm of U star equals the norm of U for every bounded linear operator? And the norm of U is 1. So this equals the absolute value of lambda, and then okay, and this equals the absolute value of lambda, and this is less than 1. Okay, so you can see here, less than 1. This is less than 1. So lambda U star is an operator of norm less than 1. Then by this proposition, if you remember 3.7, since this is an operator of norm less than 1, then 1 minus lambda U star is invertible. Okay, because the norm of this one is less than 1. So I minus lambda U star by this proposition is invertible. U is also invertible, right? Because U is a unitary operator, and the inverse of U is U star. So this is invertible. U is invertible. So the product of two invertible operator is invertible. But the product of these two becomes U minus lambda I. Okay, this is U star is I. So this is invertible. This is invertible. The product of these two, which is U minus lambda I, is invertible. But when you say U minus lambda I is invertible, what does it mean? It means lambda does not belong to a spectrum. Okay, and this is a contradiction, and this contradiction is coming from this assumption. You suppose that the absolute value of lambda is less than 1. So this doesn't happen. This doesn't happen. So the absolute value of lambda must be equal to 1. Okay, so this completes the proof. Okay, look at here. This exercise is empty, nothing here. I just want to give you some indication how to prove the norm of U equals 1. Look at here. The norm of U u of x squared. So u of x is an element of the Hilbert space. It's defined to be the inner product of ux and ux. And this equals by the property of the adjoint operator, the inner product of x and u star ux. Okay. Do you remember, like you view this as y? Okay, so ux, the inner product of ux, and y equals the inner product of x and u star y. But our y is this. Now, u star u equals identity operator, right? Because u is unitary. So this becomes the inner product of x and x, which is the norm of x squared. So from this we get, if you take a square root on both sides, the norm of ux equals the norm of ux equals the norm of x. You can use this, okay, to show that the norm of u is 1. So this is an indication for you.